In this chapter, we're going to look at light and optics. We're going to start with the history of light. History of light. The first scientist to make a prediction about light was Isaac Newton, and he said light is made up of corpuscles or particles. So Isaac Newton stated that light is made up of corpuscles or particles. And then later it was found out that light displays wave properties such as diffraction, refraction, so on. And a scientist by the name Christian Huygens states that light is a wave. A scientist by the name Christian Huygens stated that light is a wave. And then later, in the mid-18th century, the wave nature of light was firmly established by Maxwell, who developed Maxwell's equations. And later, in the mid-1800s, the wave nature of light was I should say firmly established by a scientist by the name Maxwell, who developed the Maxwell equations, Maxwell's equations. But then in the late 1900s and early 2000s, some experiments were done that contradicted the wave nature of light. Okay, in the late 1900s or early 2000s or early 2000s, some experiments that contradicted wave nature of light were done. These experiments are experiments such as the photoelectric experiment, the Blackbird radiation experiment, and so on. So the current understanding of light is that light is both particle and a wave. So the current understanding of light is that it is both particle and a wave. What this means is, in some properties it displays, in some experiments it displays particle properties, and in some experiments it displays wave properties. So this is briefly the history of light. The first scientist to make a prediction about the history of light was Isaac Newton, and he stated that light is made up of corpuscles, but later it was found out that light displays wave properties, and so Christian Huygens concluded that light must be a wave. And then in the mid-1800s, a scientist by the name Maxwell developed so-called Maxwell's equations, and based on those equations he was able to predict that light along with other electromagnetic waves is a wave. But in the late 1900s or early 2000s, some experiments that contradicted the wave nature of light were done. So the current understanding of light is that it's both a wave and a particle, which means in some properties it behaves, in some experiments it behaves like particles, and in some experiments it behaves like particles. So we're going to look at the wave nature and particle nature of light separately. So let's look first at the wave nature of light. Wave nature of light. This is based on Maxwell's equations. This is based on Maxwell's equations. Maxwell was able to interpret all the experimental findings in his era into 4 equations called Maxwell equations. Actually, I've already discussed all of them in this course so far, so let me state the equations. So let me state what Maxwell's equations are. Maxwell's equations. The first one is Coulomb's law. This deals with the force between charged objects, Coulomb's law. This deals with the force between charged objects. If you remember, we said that the force between 2 charged objects is inversely proportional to the square of the distance separating them and directly proportional to the product of the charges. So the first Maxwell equation is basically a statement of this law. The second one is called Gauss law for magnetic field. Gauss law. This is basically a statement of the fact that magnetic field lines form complete loops. This is a statement of the fact that magnetic field lines form complete loops. This is a mathematical statement of the fact that magnetic field lines form complete loops. If you remember, electric field lines, they originate in a positive charge and in negative charge, but magnetic field lines, they form complete loops, and this is a mathematical statement, the fact that magnetic field lines form complete loops. And the third one is called Ampere's law. This is a statement of the fact that current gives rise to magnetic field. Okay, so this is a statement of the fact that magnetic field, current or motion of charges gives rise to magnetic field. And this was also modified theoretically by Maxwell. So this was modified theoretically by Maxwell to include the fact that the rate of change of electric field also gives rise to magnetic field. The rate of change, the variation of electric field with time, gives rise to electric field, to magnetic field. So these are the meaning of the 4 Maxwell's equations. the first Maxwell equation has to do with the fact that charges exert force on each other, and the second law, second Maxwell's equation, is stating the fact that magnetic field lines form complete loops, and the third one is a statement the fact that current gives rise to magnetic field, which was modified by Maxwell to include the fact that the rate of change of electric field also produces magnetic field. The first one is Faraday's law. Faraday's law. Faraday's law. This is a statement of the fact that the rate or the variation of the magnetic field with time gives rise to electric field. So this is a mathematical statement of the fact that the variation of magnetic field with time gives rise to electric field, or you can say induced voltage, electric field or induced voltage. So Maxwell was able to condense all the experimental findings in his era into these four Maxwell's equations, and by combining these four equations he was able to predict that whenever a charge is accelerated, electromagnetic wave is propagated. Okay, so by combining these equations, Maxwell was able to predict that whenever charges are accelerated, electromagnetic wave is propagated. Electromagnetic wave is propagated. Okay. For example, all these radio stations and television stations, so on, if they want to send signals to our house, all they have to do is accelerate some charges. Their acceleration of charges will propagate electromagnetic waves. Okay. And the speed of all electromagnetic waves is the speed of light. The speed of all electromagnetic waves is the speed of light. We're going to use C for the speed of light, and that is I should say this is in vacuum, and the value of C is 3 times 10 to the power of 8 meters per second. So he was able to theoretically predict that the speed of all these electromagnetic waves is 3 times 10 to the power of 8 meters per second, or the same as the speed of light. So you conclude that light must be a subset of electromagnetic waves. Maxwell predicted that light must be a subset, let's say a small subset of electromagnetic waves, Okay, so let's look at some examples of electromagnetic waves. Examples of electromagnetic waves. Okay, as we just stated, we have light, which gives us sensation of light. sensation of vision, sensation of vision. We have infrared wave, which gives us sensation of heat, gives us sensation of heat. We have ultraviolet radiation. You can say this produces vitamin D in our body, produces vitamin D in our bodies. Okay. We have X-rays. These are used in hospitals to produce images of our bones. Makes pictures of our bones because it can penetrate the flesh or our body and stopped by denser parts of our body. So that's how it's able to make pictures of our bones. We have let's say radio waves. These carry radio signals. They carry radio signals. And then we have gamma radiation, which is the most energetic radiation, So these are some examples of electromagnetic waves. So as you can see, light is only a small part of this wide range of waves that we call electromagnetic waves. All right. Now, since electromagnetic waves are waves, they satisfy the wave equation. Okay. So since electromagnetic waves are waves, okay, they satisfy the equation. The equation speed equals frequency times wavelengths. Okay. Now the speed of all electromagnetic waves is c. So with the following equation, c equals frequency times wavelengths. Okay. So of course in this equation, c is 3 times 10 to the power of 8 meters per second. F stands for frequency, or the number of cycles per second, and the wave lambda represents the wavelengths, which is the distance traveled in one cycle or in one period. Okay. Now, if you remember, a wave is a physical quantity in which certain physical quantity varies as a function of position in time. In this case, in the case of electromagnetic waves, the physical quantities that vary as a function of position in time are electric field and magnetic field. Okay. So in the case of electromagnetic waves, let me just use EM, electromagnetic waves. The physical quantities that vary, as a function of position in time, are electric field and magnetic field. So electromagnetic wave is simply a propagation of electric field and magnetic field in space. Okay. Now, some properties of electric field and magnetic field. Electric field and magnetic field are always perpendicular to each other and to the direction of propagation of energy. and magnetic field are always perpendicular to each other, always perpendicular to each other, and to the direction of propagation of energy, to the direction of propagation of energy. Okay, let's say we have this coordinate system over here. Let's say this is the direction of propagation of energy. Let's say this is direction of propagation of energy. That is, the wave is traveling in this direction of energy. And then let's say the electric field is varying like this. Then the magnetic field will go like this, perpendicular to it. Okay, let's say this is the electric field. Let's say this is E, and the magnetic field will go parallel to this one, will go like this, and so they'll be perpendicular to each other. Okay, so let's say this is the x-axis, so the magnetic field will vary along the x-axis, and the electric field will vary about the z-axis. So if this is going in the z direction, then you've got electric field varying along the z-axis, and the electric field varying along the x-axis. Okay, so electric field and magnetic field are always perpendicular to each other, and in vacuum the speed of propagation is the speed of light, which is 300 million meters per second. Okay, so this is the wave nature of light briefly. Maybe let's consider an example. Let's say calculate the frequency of red light, let's say whose wavelength is 700 nanometer. Okay, so we're told the wavelength is 700 nanometer. Remember, nano means 10 to the power of 9. Okay, 10 to the power of 9 meters. So that is 7 times 10 to the power negative 7 meters. And we know the speed of light is 3 times 10 to the power of 8 meter per second. And this is a formula: speed of light equals lambda times frequency, which implies frequency equals speed of light divided by the wavelengths. So the frequency of red light is the speed of light, 3 times 10 to the power of 8, divided by 7 times 10 to the power of negative 7 meters. Okay, it's meters per second. So we get the frequency of red light is 3/7 times 10 to the power of 15 cycles per second, or hertz. Okay. Now we're going to look at the particle nature of light. Particle nature of light. This one is based on an experiment called the black radiation experiment, which was done in the late 1900s by Max Planck, a German scientist, Max Planck. So let me describe the black radiation experiment first. The black radiation experiment. Radiation experiment. So when an object is heated, it emits all kinds of wavelengths, and an experiment was done to see the intensity distribution of the electromagnetic waves of different wavelengths emitted by the object. Okay, so when an object is emitted, is heated, it emits all kinds of wavelengths of electromagnetic waves, lengths of electromagnetic waves. So this experiment is an experiment done to study the intensity distribution of this electromagnetic waves. Okay, so the intensity distribution of the wavelengths Now, when they did the experiment, they get a curve that looks something like this. Let's say these are the different wavelengths emitted by the hot object, and let's say this is the intensity corresponding to each wavelength. So the experiment showed that the intensity distribution is very low for low wavelengths, and then it reaches a maximum at a certain wavelength, okay, and then it decreases, something like this, okay. So this experiment showed that the intensity distribution starts very low and then reaches a certain maximum value, and then for large wavelengths it keeps decreasing. So scientists were trying to explain this experiment using classical physics, basically, which means Maxwell's physics. But classical physics failed to explain this experiment. They were able to fit this side over here, goes like this, but it never comes back. They were also to explain this side of the experiment, but it never comes back. Okay, they were never able to predict this turning point of the intensity as a function of wavelengths. So classical physics, which means Maxwell's physics, failed to explain this experiment. Failed to explain this experiment. The black body radiation experiment. Black body radiation experiment. And so another theory has to be developed. If a theory fails, then you have to develop another theory. And the scientist that came up with a new theory to explain this experiment was the German scientist Max Planck. Okay, so the German scientist Max Planck, he has to make the following two postulates to explain this experiment. Was able to explain the experiment with the following two postulates. Okay, the first one says light is propagated in the form of particles that we call photons. The first one is light is propagated in the form of particles that we call photons. Okay, so you see, the wave nature of light was firmly established by Maxwell, but now Maxwell has to assume that light is propagated in the form of particles to explain this experiment. Okay, and the second postulate is the energy of a photon is proportional to its frequency. The energy of a photon is proportional to its frequency. Okay, so if you use E for energy of one photon, according to this postulate, the energy is proportional to its frequency, which means the ratio between the energy and the frequency is a constant. And by fitting his curve to the experimental graph, he was able to come up with the following number. This constant is 6.6 times 10 to the power of negative 34 joule second. Okay, and this constant is denoted by h, which is called Planck's constant, by h, which is called Planck's constant, which is called Planck's constant. So we have the following. This is a formula Planck came up with: h times frequency. Okay, and if there are n photons, obviously just add them up. If there are n photons, obviously En would be n times h times f. Okay, so this is the formula Planck came up for the energy of a photon. So he's saying that light is made up of particles, and the energy of a photon or photons given by this formula. So you see, this formula embodies both the particle nature and wave nature of light. This n, which is numbers ring count, which is a particle property, indicates that light has particle properties. But then you have also this frequency, which is a wave property. So this equation embodies both the particle nature of light and the wave nature of light. Okay, so let's revise. An experiment was done to study the intensity distribution as a function of wavelengths when an object is heated, and experimentally they were able to come up with this graph. Okay, it starts low for low wavelengths and then reaches a certain maximum certain wavelengths, and then keeps decreasing to very low intensity for how high wavelength radiation. Now, classical physics was not able to explain this experiment. They were explained to explain this side, but then never comes back. They were also explained to they were able to explain this side, but then never comes back. They were never able to explain this turning point for the intensity distribution of the different wavelengths. So a new theory has to be developed, and the scientist that developed the new theory is the German scientist Max Planck. To explain this experiment, he made two postulates. He said light is propagated in the form of particles that we call photons, and the energy of photon is proportional to frequency. All right, so that's how the particle nature of light was started in the late 1900s or early 2000s. But when Maxwell developed these theories, people thought it was just a mathematical trick. But later, an experiment called the photoelectric experiment was done that proved this theory of Maxwell, and then was taken seriously. And of course, it's now it led to the creation of a new type of physics called quantum mechanics. All right. So these are briefly the wave nature and particle nature of light. Maybe let me add one example. Let's say calculate the energy of, let's say, 1000 photons of red light whose wavelength is 700 nanometer. Okay, so we want to calculate the energy of 1000 photons of red light. So the number of photons is 1000, and we're told the wavelength is 700 nanometer, or 7 times 10 to the power negative 7 meters. Okay, and we want to calculate the energy of 1000 photons. Okay, that is E 1000 equals 1000 times Planck's constant times frequency. But we don't have frequency, we have wavelengths, but we know that frequency equals speed of light divided by the wavelengths. Okay, So the energy of the 1000 photons equals 1000 times Planck's constant, and then this is speed of light divided by the wavelengths. Okay, so this is 1000 times Planck's constant, 6.7 times 10 to the power of negative 34, and then we have 3 times 10 to the power of 8 for the speed of light, and then the wavelength is 7 times 10 to the power of negative 7. Okay, so from the numbers we have 6.6 times 3 divided by 7. Okay, and then for the parts we have negative 34, we have 15 over here, 15, and then this one is 18, so that is times 10 to the power of 16, negative 16 joules. So this is the energy of 1000 photons of red light. All right, now we're going to look at properties of light. Properties of light. First, we're going to look at reflection. Reflection is the bouncing of light from a surface. This is bouncing of light from a surface. Okay, from a surface. So let's define some terms. Suppose this is the surface over here. Okay, suppose light is hitting the surface at this point over here. So this light is hitting the surface at this point. Okay, and let's say it's bouncing back like this. Okay, now this light over here is called incident light, incident ray. Okay, this one is the reflected ray, Now in optics, angles are measured with respect to the line perpendicular to the surface at the point of impact. This line over here, which is perpendicular to the surface, is called the normal line. Okay, this line is very important because angles are measured with respect to this line. So the angle of incidence is angle formed between the normal line and the incident ray. Okay, so we call this one angle of incidence. Angle of incidence. Okay, and the angle made between the reflected ray and the normal line, this one over here, is called angle of reflection. Angle of reflection. Now the law of reflection has to do with these two angles. Let's say this is angle of incidence. Let's say this is angle of reflection. Okay, experiment shows that these two angles are equal. The angle of incidence and angle of reflection are equal, and that's called the law of reflection. So law of reflection states that the angle of incidence is equal to angle of reflection. Okay, that is angle of incidence equals angle of reflection. That's what we call the law of reflection. And remember, angles are always measured with respect to the normal line, which is a line perpendicular to the surface at the point of impact. Okay, so that's what we call the law of reflection. So let's look at some examples. Suppose we have this surface over here, and let's say we have light incident on this surface. Let's say this angle is 30 degrees, this angle over here, and then we have the normal line over here. Okay, and then let's say it goes back like this, and we want to calculate the angle of reflection. The question is calculate the angle of reflection. The angle of reflection, that is theta r. Okay, so we know that angle of incidence equals angle of reflection, so these two angles are equal. Okay, so this is the angle of incidence, but we know that the sum of these two angles is 90 degrees. Okay, so we have theta I plus 30 degrees equals 90. That tells me the angle of incidence is 60 degrees, and then the angle of reflection equals the angle of incidence, that is 60 degrees. Okay, so the angle of reflection in this case would be 60 degrees. Another example. Suppose we have, let's say, the following two mirrors. These are mirrors. Let's say this angle over here is maybe 100 degrees. Okay, now suppose we have a light ray hitting the surface, let's say at an angle of 40 degrees, and then goes to the other mirror, and then it's reflected from that other mirror. Okay, so we want to calculate this angle over here. It's called x. Okay, so we've got two mirrors at an angle of 100 degrees. So this light ray goes like this, following the law of reflection, and we're going to calculate this angle over here. So the question is calculate x. Calculate x. Okay, so we're going to start over here. This is the normal line, so this is 90 degrees, therefore this is going to be 50. Angle of incidence equals angle of reflection. This angle is 50, therefore this angle over here is 90 minus 50. This angle is 40. Okay, but we've got a triangle over here, and the sum of the angles of a triangle is 180 degrees, right? So this is 100, this is 40, their sum is 140, so this angle over here is 180 minus 140, or 40 degrees. Okay, and then you come back to this normal line over here. If this angle over here is 40, then this angle is 50. But these two angles are equal, they're 50. If this angle is 50, x must be 40. Okay, so you can just keep applying the law of reflection to calculate this angle. All right, the next property is refraction. Refraction. Refraction is the bending of light as light crosses the boundary between two mediums. This is the bending of light, the bending of light as light crosses the boundary between two mediums. The boundary between two mediums. Let's say we have this boundary between air and water. Let's say this is air, and then we've got water over here. Okay. Once again, angles are measured with respect to the normal line, the line perpendicular to the boundary as a point of impact. Okay. So let's say light comes this way over here. Okay. When it goes through, it's going to bend. This is what you call refraction. Refraction is the bending of light as light crosses the boundary between two mediums. This is the boundary between two mediums with different optical densities. Now, this ray over here is called the incident ray. Incident ray. This light over here is called the refracted ray. Refracted ray. Okay, and this angle over here, the angle between the normal line and the incident ray, this one is called angle of incidence. Angle of incidence. All right, and this angle over here is called angle of refraction. Angle of refraction. So remember, in optics, angles are measured with respect to this line, respect to the line. normal to the surface at the point of impact. Okay. So next we're going to define what we mean by refractive index of a medium. Refractive index of a medium. We're going to use n to represent it. Okay, it's the refractive index of a medium. Okay, first let me state that as light crosses from vacuum or air to another medium, the speed of light and the wavelengths decrease while frequency remains the same. Okay, so let me state that as light enters a medium from vacuum, which could be approximated to be air, okay, the speed of light, and wavelengths decrease, lengths decrease, while frequency remains the same because of conservation of energy. While frequency remains the same. Remember, frequency is a measure of energy. So the frequency remains the same, but the wavelength and the speed will change. So what we call refractive index is the ratio between the speed of light in vacuum and the speed of light in the medium. Okay, so that's how it's defined. Refractive index of a medium, refractive index of a medium is defined to be the ratio of the speed of light in vacuum, to the speed of light in the medium, to the speed of light in the medium. Okay, so let's say it's a boundary between, let's say it's vacuum or approximately air, and this is a certain medium M. This is M represented. Okay, so let's say this is our normal over here. So you've got light coming this way, light coming this way. So the speed over here is going to be C. Let's say the speed over here is going to be the speed of the medium. Okay, so the refractive index of the medium is defined to be the speed of light divided by the speed in the medium. So the refractive index of the medium is the speed of light in vacuum divided by the speed of light in the medium. All right, so that's how refractive index is defined. Now remember, when light enters any medium from vacuum, the speed decreases. So that tells you this number is greater than 1. It's equal to 1 for vacuum or approximate air, because this will be C, but it will be greater than 1 for any other medium. Okay, so refractive index is equal to 1 for vacuum, approximately air, and greater than 1 for all mediums, for all other mediums. Now I'll give you a couple of numbers we're going to use very often. The refractive index of glass is 3/2 or 1.5, and the refractive index of water is 4/3. We're going to use these numbers very often. Okay, we can also write this in terms of wavelengths. Remember, frequency remains the same. Frequency doesn't change. Okay, so we have for the vacuum, this equals frequency times the wavelengths in vacuum, and the speed in the medium is the frequency times the wavelengths in the medium. Okay, so the refractive index in the medium, which is speed of light, divided by the speed in the medium, equals frequency times wavelengths in vacuum divided by frequency times wavelengths in medium. Okay, this the frequency cancels out, so we have also the following formula. So the refractive index for medium is the wavelengths in vacuum divided by the wavelengths in the medium. Okay, so this is an expression for the refractive index in terms of wavelengths. Okay, so lambda v is wavelengths in vacuum and lambda m is wavelengths in medium, medium. Okay, example, let's say violet light has a wavelength of 4 times 10 to the power of -7 meters in vacuum. Okay, calculate its wavelengths, let's say in water. Okay, so lambda v for violet light is 4 times 10 to the power -7. We won't calculate the wavelengths in water. Okay, but we know that the refractive index of water is 4/3. Okay, so we have the refractive index of water equals wavelengths in vacuum divided by wavelengths in water. Okay, so this tells you the wavelengths in water is the wavelengths in vacuum divided by the refractive index of water. Okay, so that is 4 times 10 to the power -7 divided by the refractive index in water. Okay, so that is looks like 3 times 10 to the power -7 meters. All right, now let's say calculate the speed of light in water. Okay, so we have refractive index of water equals speed of light in vacuum divided by the speed of light in water. Okay, that's the refractive index. All right, so we just have, this is 4/3, right? This is 4/3. So you've got the speed of light in water equals speed of light in vacuum divided by refractive index in water, right? So that is 3 times 10 to the power of 8 divided by 4/3, which is 9/4 or 2.25 times 10 to the power of 5 meters per second. All right, so this is the definition of refractive index. Refractive index is basically a measure of the optical density of the medium. The greater the density, the greater the refractive index. Okay, now we're going to look at law of refraction. Law of refraction is called Snell's law. It's called Snell's law. Okay, suppose let's say we have the medium between, the boundary between, let's say this is medium 1, let's say this is medium 2. medium 2. Okay, suppose this is the normal line over here, like this. So let's say we've got light coming this way, and then it's refracted. Let's say it goes like this. Okay, so let's call this angle of incidence over here. Let's call this theta 1, angle in medium 1, and let's call this theta 2. Okay, now experiment shows that the ratio between the sine of this angle in medium 1 and the sine of the angle medium 2 is a constant, and it's equal to the ratio between the speeds of light in the respective medium. Okay, so experiment shows that the ratio between the sine of theta 1, that is, and sine of theta 2 is a constant. And is equal to the ratios between the speeds of light in the respective mediums, Okay, so let's say the speed of light over here is b1, the speed of light over here is b2. Okay, so this is the speed of light in medium 1 and this is speed of light in 2. All right, so what this says is the ratio of sine of theta 1 divided by sine of theta 2 equals speed of light medium 1 divided by speed of light in medium 2. All right, now we can express in terms of refractive index. Okay, so remember, v1 is speed of light divided by refractive index in medium 1, and v2 is speed of light in vacuum divided by refractive index in medium 2. All right, so we have the sine of theta 1 divided by the sine of theta 2 equals speed divided by the refractive index in medium 1, and then speed in vacuum divided by the refractive index in medium 2. Okay, so the c's cancel out. Basically we'll get this one, sine theta 1 over sine theta 2 equals n2 divided by n1. This is what we call Snell's law. Okay, this is Snell's law. This is what we call Snell's law, or law of refraction. The ratio between the sine of angles of medium 1 and medium 2 equals to the ratio between the refractive index of medium 2 to the refractive index in medium 1. But probably this one is easier to write like this. If you cross multiply, let's make it more symmetric. Let's put the 1's on one side and the 2's on the other side. So this is an easier expression for Snell's law. Okay, so this is what we call Snell's law. Okay, let's look at an example. Let's say we have the following situation. Let's say it's the normal line over here. Okay, let's say this is air. Let's say this is water. Okay, so let's say we have this incident light. Let's say this is maybe 60 degrees, and let's say it goes like this, and we want to calculate this angle over here. Okay, that is theta 2. Let's say, well, it's going to be theta water. We want to calculate this. Okay, so we're going to use Snell's law. That's going to be the refractive index of air times the sine of the angle in air equals refractive index of water times the sine of the angle in water. Okay, the refractive index of air is approximately 1. This is 1. The refractive index of water is 4/3. And then the angle in air with respect to normal is given to be 60 degrees. We have to calculate the angle in water. Okay, so applying the numbers, 1 for air, the sine of 60 equals n of water is 4/3, the sine of theta in water. Okay, so the sine of the angle in water equals 3/4 times sine of 60. Okay, so sine of 60 is root 3/2. Okay, so we have the angle in water is the sine inverse of this expression, 3/4 times root 3/2. Okay, so this will give us the angle of refraction in water. Now I see this is a less dense medium. It's going to a more dense medium. Now, as you go from from a less dense to a more dense medium, you see you're going from high speed to low speed. And so the ratio would be a large number divided by a small number. Okay? And that tells you that the angle of refraction over here decreases as light enters from a low dense medium to a high dense medium. Okay, so let me state this, as light enters a more dense medium, it bends towards the normal. It bends towards the normal. And if it's going the other way, as light enters a less dense, which means smaller refractive index, dense medium, it bends away from the normal, Okay, so we're going to go to air. Air has a refractive index of 1, this one's 4/3, so this one is entering a more dense medium. Okay, so this will bend, you see it's going this way, will bend towards the normal. Okay, if it's going the other way, let's say it's going this way, then you see it's going to bend away from the normal. Okay, and you can see that using this formula over here. Okay, if you're going to a less dense medium, okay, so this number would be let's say you're going from high dense to low dense, this number will be smaller, so this number has to be bigger, smaller to make this one bigger. All right. Now we're going to look at dispersion. Dispersion is the separation of white light as light enters a medium from a vacuum. This is separation of white light into 7 different colors, 7 different colors as light enters a medium from vacuum or air. From vacuum or air. Okay, so let's say this is vacuum or air, and then let's say this is our normal over here. So what this is if you've got light coming this way, this will split in 7 different colors. 1, 2, 3, 4, 5, 6, 7. Okay, I'll split into 7 different colors. These colors arranged in increasing wavelengths are arranged in an increase, arranged in ascending wavelengths. That's going from low to high, and ascending wavelengths. These colors are, they are violet, indigo, blue, green, yellow, orange, and red. Maybe it'll be easier to remember them by the initials. Okay, that's B, Gior. Okay, violet, indigo, blue, green, yellow, orange, red. This is in an increasing order of wavelengths. Violet has the lowest wavelengths, red has the largest wavelengths. Okay, this is in increasing order of wavelengths. Increasing order of wavelengths. Okay, so violet has the smallest wavelengths and red has the largest wavelengths. So why does white light split into different colors? Well, first of all, it's a mixture of 7 different colors, but as light enters a medium, the refractive index is a function of the wavelengths. The medium has different refractive indexes for different wavelengths. So the reason white light splits into different colors is because the refractive index is a function of wavelengths. Actually, it decreases with an increase of wavelengths. It decreases with increase of wavelengths. Increase of wavelengths. So what that means is, since violet has the smallest wavelengths, it has the largest refractive index. This implies violet has the largest refractive index because it has the smallest wavelengths, and then of course red will have the smallest refractive index because it has the largest wavelengths. Okay, red has the smallest refractive index, because it has the largest, it has the largest wavelengths. Okay, so the one with the largest refractive index will bend the most. Okay, so that means violet will bend by the largest angle, red will bend by the smallest angle. So this implies violet will deviate from its original path by the largest angle, and red will deviate by the smallest angle. Okay, so if you look at this diagram over here, this would be violet, will deviate by the largest angle, and this would be red. Okay, and the others in between in increasing order of wavelengths. So it goes violet, indigo, and so on in this direction until you get red. All right. Example. Let's say refractive indexes of red and violet light in glass are, let's say, 1.48 and let's say 1.52 respectively. So for a certain glass, the refractive index is 1.48. The refractive index for violet is 1.52. The question is, as light enters the glass from vacuum, let's say at an angle of incidence, let's say of 80 degree, calculate the angle between violet and red light. Okay, so that's what we have. We have this is vacuum over here, which means refractive index equals 1 over here, and vacuum is 1. And then let's say it's a normal line over here, and this medium is glass. Okay, so this is entering at an angle of incidence of 80 degrees. Okay, so the different colors are going to bend by different angles. So let's say this is red, and let's say this is violet. This is violet. Okay, red, violet. All right, so we calculate this angle first. Is theta violet over here, and this angle is theta red over here. So we're looking at this angle. It's called theta. Okay, so theta equals, oh no, theta red is, this is theta red over here, this is theta over here. Okay, this is theta red, this is theta over here, and theta over here. So you get theta red minus theta violet would be this angle we're looking at. Okay, so you just have to calculate the angle for red and the angle for violet. Okay, so first let's work out for violet. For violet, we have refractive index of vacuum, sine of angle in vacuum equals, maybe let me put air over here, let's confuse this one. So this is air or vacuum. Okay, so this is violet, and then This is sine. This is air, and this is glass. Okay, and this is for violet. All right, so we've got 1. This sine of 80 equals refractive of index of violet, which is 1.52. Okay, and then sine of theta and glass. Well, let me put a V over here. Glass, V over here. All right, so you've got the sine of the angle in glass for violet is sine of 80 divided by 1.52. Okay, so the angle in glass for violet is sine inverse of sine of 80 divided by 1.52. Okay, and then we do the same thing for the angle in glass for red. So you've got refractive index of air, sine of the angle in air, this is for red, equals refractive index for red, and sine of angle in glass for red. Okay, so you've got 1 sine of theta air for red equals, and that's 1.48, and well, this one is 80. Anyway, the sine of theta glass and red. Okay, so this one is 80. So you've got the sine of theta in glass for red is the sine of 80 minus 1.48. Okay, so the angle in glass for red would be sine inverse of sine of 80 divided by 1.48. Okay, and then of course the angle is the difference in the two, right? So you've got theta in glass for red minus theta glass for violet. Okay, so for red it is sine inverse of sine of 80 divided by 1.48, and then minus the sine inverse of sine of 80 divided by 1.52. Okay, so this will be the angle between violet and red. Finally, we're going to look at total internal reflection. Total internal reflection. Now, as light hits a boundary between two mediums, most of what's going to happen is some of it will be reflected, some of it will be refracted. Okay, so as light enters a medium, most of the time some of it will be reflected and some of it will be refracted. But there is a special situation where only reflection takes place, and that's what we call total internal reflection. But there is a special case. There is a special case where only reflection takes place, called total internal reflection, called total internal reflection. Okay, so most of the time that's what's going to happen. Some will reflect, some will be refracted. For example, let's say you have light rays hitting water. Okay, let's say this is water. Okay, Now let's say the normal line over here. So if you've got light rays, let's say this is air over here. If you've got light rays coming this way, what's going to happen is some of it will be reflected like this, and some of it will be refracted. Okay. You see, you can see your water. I mean, you can see your face in water. That's possible because some of the light rays are reflected. It means the water surface is acting as a mirror. But also you can see objects inside the water because some of the light rays are being refracted to the object inside the water and then coming back to you like this. So that tells you this light ray, some of it is reflected and some of it is refracted. The fact that you can see your face in the water tells you some of the light rays have been reflected, and the fact that some you can see objects inside the water tells you some of it is being refracted. Okay, but now let's look at the special situation where only reflection takes place. Okay, now as you've seen before, as light enters a less dense medium, it bends away from the normal, right? So let's say this one has a smaller refractive index, this one has a greater refractive index. As light enters a less dense medium, it bends away from the normal. I'll go like this. Okay, so for this situation, what can happen is some of it would be refracted and some of it would be reflected. Okay, what happens if you keep increasing this angle? Well, we'll keep bending towards away from the normal, but for a certain special angle over here, it will go parallel to the surface. Okay, this is what you call the critical angle. This is called the critical angle. We're going to use theta c to represent it. So this angle is the angle for which the light ray is refracted parallel to the surface. But then what happens for angles bigger than this one? You see, the only process can take place for these angles is reflection. Okay, so you've got a light ray over here, refraction is not a possibility, it's just reflected. Okay, so on this range only reflection can take place, that is only total internal reflection takes place. Okay, so in this range over here, both reflection and refraction can take place. Okay, you got a light ray like this, it can bounce back or it can go, or it can be refracted. But if the angle is bigger than the critical angle, then the only possibility is reflection. Okay, so as light enters a less dense medium, as light enters a less dense medium, it bends away from the normal. And for a certain angle, angle called the critical angle, theta c, the light ray is refracted parallel to the boundary. For angles bigger than theta c, only reflection is possible. For angles greater than theta c, only reflection is possible. Which we call total internal reflection. Okay, so if theta is less than theta c, both reflection and refraction take place. refraction take place. If theta is bigger than theta c, then only reflection or total internal reflection takes place. Total internal reflection takes place. Reflection takes place. Okay? Now let's try to obtain expression for the critical angle when the angle of incidence, or when theta greater equals theta c, theta less equals 90 degree. Okay, so using Snell's law, we've got n less sine of theta less equals n greater times the sine of theta greater. Okay, so we have n less, this one is 90 degree, equals n greater times the sine of theta greater, not theta c. This one is the critical angle. Okay, sine of 90 is 1, so you've got n less equals n less over n greater equals sine theta c, or we have theta c equals sine inverse of n less over n greater. Okay, so that's how we calculate the critical angle. Example, let's say calculate the critical angle between the water glass boundary. So in this case, water has smaller refractive index, so that's 4/3. Glass has a greater refractive index, which is 3/2. Therefore, the critical angle for this boundary is sine inverse of n less, which is 4/3, divided by n smaller. Okay, so that is sine inverse of 8/9.